landing with a speed of 115 meters per second, and the plane has a maximum braking acceleration of 7.42. Okay, what is the minimum time interval that is needed for the plane to stop? Okay, if we draw this out here, we'll have a plane coming in with a speed of 115 meters per second. There's going to be a runway here of some small length because it said it was short. What else is going on? It's maximum braking, so I know the acceleration of the plane is slowing down, which means my acceleration here is 7.42. Has to be negative because it is slowing the plane down. Okay. What is the minimum time interval needed to stop? Those are the only numbers that were given. So let's go ahead and draw out our table. Okay. It didn't care about position. It doesn't care how long the runway is. It was never mentioned in here, except for that it was just short. The initial velocity, well, that's easy. The plane is traveling at 115 meters per second when it comes in. The final velocity, so here's wordplay in here. You have to make sure you understand the question. It needs to land on a short runway, which means it needs to stop the plane. Okay, so our final velocity, we need it to be 0. Okay, the plane needs to stop. Acceleration, we do have that acceleration. It is important that you put it in as negative, okay, because we need the plane to slow down. What is the minimum time interval needed for the plane to stop? So that's our question. We need t. We need to know t. All right, so we go back to our kinematic equations. I'm looking for something that has t in it that does not have an x in it. Okay. And the one that I come up with is the change in x is equal to VIT plus 1/2 AT. Let's go. No. Yes. No. We don't want this one. We don't want this one. This one doesn't make any sense to us. Accidents occur. We don't want that. We want something that does not have t in it. So you go back to your table and you look at something that does not have a delta x in it. And what we come across is VF is equal to VI plus AT. No x in sight. Okay. All right, so we'll go ahead and we'll punch in. VF this is a good thing though. If you do run into a problem and you go, oh, I need t for this, and I need the x in here. How am I gonna go back, start the problem back over again? Look at what you need. VF is 0. VI is 115. Acceleration, we have a negative number, 7.42. And t is just going to hang out there by itself. All right, so you've got an addition. Move that over to the other side. You'll have a negative 115. And now you have a negative times a t, so let's divide to get that over. We'll have a negative 7.42, and that whole thing will be equal to t. So a negative on a negative are going to cancel, because it would be a little weird if you had a negative time for this answer. Negative time would mean that the plane landed before, it took less amount of time for it to land rather than coming in. It just wouldn't make any sense. Okay. If you calculate that out, you should get t is equal to 15.5 seconds. Okay, and again, these are two-part problems, so this is just part A. 15.5 seconds is the time needed for the plane to come in to land. Is that real? I don't know. Next time you're on a plane, count it out. 15 seconds is actually quite a bit of time, and if they applied the brakes during the whole landing, yeah, probably pretty close. Depends on the plane, I guess, too. Moving on to B. Can this plane land on an island where the runway is only 0.8 kilometers long? Prove your answer. I do not want, yeah, I think it does. Okay, that doesn't help me at all. I need you to prove that it either makes it or it doesn't make it. So for part B, what we need to know is, given all this information, what is the change in x? Because this is the maximum amount it can brake. So this will be the shortest distance that it's able to land in. Okay, you put the brakes on max, you stop the quickest, so it's be the shortest distance it can land in. So for that, we're going to need a change in x. Okay. For a change in x, nothing really too great. I don't want to use the same problems over and over again or the same equation, so let's grab a new one this time. Let's go ahead and use the one that I was using here. The change in x is equal to the initial velocity times time plus 1/2 at squared. Because we've got everything that we need, we can actually pick numerous equations that would solve for this out of the kinematics, as long as it involves a delta x. So you'd have 3 equations you could use. But I'm just going to grab this one. Okay, I'm looking for change in x. That's what I want. Initial velocity is 115. Time we had gotten from over here, so time is going to be 15.5 plus 1/2. The acceleration was going to be a negative 7.42, and then time squared. Time again here is 15.5, and that'll get squared. Okay, this is nice and easy because it's just plugging in as is into your calculator. You don't need to move anything around. And let's find out what that change in x is. Okay, so plugging in, I got a change in x of 891 meters. So this is the minimum amount of runway that it is going to need. So if we come back up to our problem and it says, can the plane land where the runway is 0.8 kilometers? Well, 0.8 kilometers is 800 meters. Can the plane land in 800 meters? No. Okay. No. It must be 891 meters. So you could put no, not long enough. You could put no.